Hello friends, welcome to MES e-learning channel. Today we'll be solving a numerical problem that involves the Hall effect concept. Here is the problem. A sample of an extrinsic semiconductor is in the shape of a slab whose length is 5 centimeter, width 0.5 centimeter and thickness of 1 millimeter. When this slab is placed in a magnetic field of 0.6 Webers per meter square, normal to the slab, okay, a Hall voltage of 8 millivolts develops at a current of 10 milliamp. You are supposed to find the carrier density, the carrier charge density, and if the longitudinal voltage driving the 10 milliamp current is 1 millivolt, what is the mobility of the dominant carriers? So here we go. Here is the solution to this. Do try it out on your own, and if you succeed, please compare it with the solution that I am providing out over here. So first thing what we do is we try to find out first of all the carrier density. The carrier density. So this is what we have to find out first of all. That's the first thing that we have to do. Okay. But prior to proceeding over there, first of all, we will draw a diagram that will clearly indicate the dimensions of the given slab, and along with that we will also know in which direction the electric field, the magnetic field and the Hall voltage is there. So this is your BZ, which is will be your Jx, and along this direction actually this is your negative, this is your plus y, and this is your minus y. Okay, now suppose it is electrons, this is going to be on this direction, and this is going to be your Hall voltage, which is there, which will be in the negative y direction if at all the charge carriers are negative. So I am also drawing at this corner, we have to remember this triad over here. So this is your x direction, this is your y direction, and this is your z direction. At the same time, he has also given us the length of each, or the dimensions of each. So this width is 0.5 centimeter, the length is going to be 5 centimeter, and the height is going to be around 1 millimeter. Okay, fine. So this is what we have been given. So let us now, first of all, I am just putting down, I will say the data and the dimensions in the data in SI units. That's the first thing which we do. So first of all, the dimensions. So this is the length is 5 into 10 raised to minus 2 meters. The width is 0.5 into 10 raised to minus 2 meters, and the thickness is given to be 1 into 10 raised to minus 3 meters. Remember students, this is along the x direction, this is along the y direction, and this is along the z direction. So these are the dimensions in the SI unit. Now what we do is, we are now going to write down the other units also, or rather the other values that have been given to us, which is your BZ, which is 0.6 Webers per meter square. You have also been given the value of the current, which is 10 milliamps, which is going to be equal to 10 into 10 raised to minus 3 amperes. And at the same time, what you have been given is the value of the Hall voltage. Normally write it as VH, that is going to be equal to Vy. As I told you, it will be in the y direction. Okay, and this is going to be 8 into 10 raised to minus 3 volts. So now everything is in SI units, and now we proceed for the formula. The formula which we have is, the formula that we have is RH, which is the Hall coefficient, is going to be equal to Vyz upon Ix Bz. That's the formula for the Hall coefficient. Do remember, Hall coefficient is also equal to 1 upon n into q, wherein n is the carrier density and your q is the charge on each of the carriers. So over here, first of all, let us try to find out what is my RH. I know my Vy, yes. I know Z, that is the thickness. I know Ix, yes, I know that. And I also know the value of Bz. Everything I have in the SI units. So let's put those values out over here. And the values will now be 8. It is 8 millivolts. So it is 8 into 10 raised to minus 3. Z is equal to 1 millimeter, which is 10 raised to minus 3 meters. Your Ix is going to be 10 milliamps, so it will be 10 into 10 raised to minus 3 amps. And your Bz is 0.6 Tesla, which is as it is. Now, if you work this out, students, the value of this turns out to be, you can check it out, and the value actually turns out to be 1.33 into 10 raised to minus 3. Units of this are meter cube per coulomb. That is the, we can write it down out over here. This is also called as the Hall coefficient. Okay. So here's now, but yet we have not been asked the Hall coefficient, but rather we have been asked the charge or the carrier density. Of course, now since we know the Hall coefficient, I can calculate. So let us label this as equation 1 and let us label this as your equation 2. So putting the value of RH into, so from equation 2, we have N, okay, which is the carrier density. This is going to be 1 upon RH into Q. If you substitute the values over here, your N is going to turn out as 1 upon RH. We got the value of 1.33 into 10 raised to minus 3 into Q. Okay, and the Q is 1.6 into 10 raised to minus 19. Okay, and hence your N turns out to be, if you work this out, it will turn out to 4.699 into 10 raised to 21 per meter cube. Okay, or maybe approximately you can say that it is turning out to approximately, I can say it is 5 into 10 raised to 21 per meter cube. So that's your N. Is it clear? So this is your very first, this is what actually, I'm sorry for that. So this is going to be, I'll just, this is 4.699 into 10 raised to 21. Okay, and this is N, this is equal to 5 into 10 raised to, so I will just put it with, right. So this is going to be per meter cube. So this is going to be the density of the majority charge carriers, okay, in the given semiconductor sample, which is extrinsic in nature, and that is going to be 5 into 10 raised to 21 per meter cube. Now, so we have solved the first part, the A part over here. This is the answer to A. Okay. Now we go to the B part. Now to be careful out over here, students, that he is actually saying that the longitudinal voltage. Now there are two types of voltages which are actually there. There is one voltage which is speaking of out over here, and this value he is already given it to us, which is 8 millivolts. And there is another voltage which you have actually applied across this slab in this direction, so that there is a flow of electrons in, right. There is a flow of electrons. Of course, the electron flow will be in the opposite direction. The current is going to be in this direction. So there is a flow of electrons over here. So we are speaking of that voltage as 1 millivolt, and because of this 1 millivolt, we have clearly mentioned, because of this 1 millivolt right voltage that has been applied, you are having a current of 10 milliamps, and we have to now use this particular data to find out my the value of the mobility. Okay, so this is where, so we already have a ready-made formula for that. Your mu is equal to your VH, which is the Hall voltage, divided by the voltage due to which the current flows, okay, into X upon Y. Look, the dimensions that I have taken, it aligns very well with the, this is Z, this is Y, and this is X. So this is aligns very well with this coordinate system, X, Y, and 1 upon BZ. You can prove this formula. There is a different exercise for that, okay, and we will call this as 3. So now substituting the values, the respective values in this, I know the value of VH, we know that this is going to be equal to 8 millivolts, which is 8 into 10 raised to minus 3. I know the value that I am applying, the voltage value that I am applying across the X direction, and this turns out to be 0.5 into 10 raised to minus, sorry, this turns out to be, just a minute students, I am just a minute, it is not 0.5, that is 1 millivolt, okay. So that is going to be equal to 1 millivolt. So this is 1 into 10 raised to minus 3. So that's it now, into X, So the X is, that is the length of it. So you can, once again you can, X is the dimensions that I have taken along the, right. So that is going to be 5. This is going to be 5 into 10 raised to minus 2. That is going to be your value. Okay, that is actually going to be your X, 5 into 10 raised to minus 2. Okay, and so that is going to be your X. We also have your Y. Your Y is turning out to be, in this case, you already know the value for that, that is the width out over there, which is turning out to 0.5 into 10 raised to minus 2. Okay, 0.5, this is, let me put a multiplication sign over here, 0.5 into 10 raised to minus 2, and finally what we are having is 0.06 Tesla. Okay, so that is your, that will be the value of your mu out over here. So we can neatly, we can just cancel this off. Oh, sorry. So this is 10 raised to minus 3. So I can cancel this off over here. This also is cancels off, and this is going to be a neatly, this is going to be equal to 40 upon, is going to be 6 into 5, that is going to be 30, but that is going to be 0.3. So that is going to be around 40 upon 0.3. Okay, fine. So this will be, the units of this are going to be meter square upon volt per second, and this actually works out to, if you can work this out, okay, it works out to, the value of mu works out to 133.33 meter square per volt second. So this is the unit of your, okay. So this is it students, and this will be your mobility. Once again, let me remind you that the Hall voltage, which is there, is 8 millivolts, it has been given to you. The dimensions along the X, which is the length of it, that is going to be 5 into 10 raised to, that is 5 centimeters, so it is 5 into 10 raised to minus 2, then divided by Vx, which is going to be 1 milliamp, sorry, 1 millivolt, and that this is Y, which is the width of it, which is 0.5 centimeter, right. So when I work on with all this, it turns out to be 133.33 meters square per volt. So this is your answer B. Okay, so I hope you like this solution. You can try it on once again and refer to this solution. Okay, and this is how this entire problem is to be solved. Thank you.